Hello, honors physics students. Let's start with problem 17, where we left off in last class. Okay, so just refresh your memory where we were, read the problem to yourself again, and pause the video, see what you've done so far. Okay, so in class you should have already drawn the picture of the light going from the liquid into the air. And as we discussed in class, you should have the air over the liquid, because really, I don't know what it would look like otherwise with the liquid sort of suspended in the air. It doesn't make a whole lot of sense, right? And if you didn't do that, please fix your picture. The picture should make sense. And I encourage you to make predictions as to what would happen, how light would refract. So we say, as light goes from liquid into the air, is it speeding up or slowing down? And well, it's going to air, which is closer to a vacuum, so we definitely know it's going to be speeding up. So then you say, well, does that mean it's going to be bending towards the normal or away from the normal? And you'll recall that as anytime light speeds up, it bends away from the normal. So hopefully that's what you drew. All right, so now it's time to do the problem. So letter A, you want to find the refracted angle when it emerges into the air. So we're thinking, of course, using Snell's law. N1 sine theta 1 equals N2 sine theta 2. But then you realize we're missing some information, right? For the air, we know the index of refraction, no problem. But for the liquid, we don't know what N is. And it just says liquid, so we can't just look it up on a table and look it up in the textbook, right? So our goal first is to find the index of refraction. Luckily, we have an equation for that. N equals C over V. The problem is we don't have V, right? We're not given the speed of light in this liquid. So really the first thing we want to do is find the speed of light in this liquid. So we look at what's given here, and we realize that we can use V equals F lambda. Now notice right away I'm not writing C equals F lambda naught, because that is lambda naught, which is the wavelength in vacuum, or air, since air is very close to a vacuum. And we're not looking for that, right? We're looking for the speed using the wavelength in the liquid. It even says it's the wavelength of 313 nanometers in the liquid, right? So we're not writing C equals F lambda naught. This is V equals F lambda. So you put your numbers in. We have the frequency, no problem there. And then we want to put the wavelength in, but notice it is in nanometers. We can't use it in nanometers. We have to convert it to meters. And certainly we could do a unit conversion. Remind yourself what the power of 10 is for nano. It's 10 to the negative 9th. Nano, 9, even sounds like it. But an easier way to do it is this. Just write 313 and then replace nano with its power of 10. So we write it like this. 313 times 10 to the negative 9th. So here we're replacing nano. It is a much easier way of doing it. I strongly suggest you do it this way, because otherwise if you do a unit conversion, start moving the decimal point around, you might lose track of the zeros, you might do something wrong, but this will take care of all that, right? So just write it as 313 nano, or times 10 to the negative 9th meters. So you put the numbers in, we get our speed, and we should be getting this, 2.5 times 10 to the 8th meters per second. Okay, that's expected, right? It's certainly slower than the speed of light in vacuum, but still really fast. All right, remember our next step is to find the index of refraction. So hopefully we could use N equals C over V. Notice here I'm using N1 equals C over V1, right? Because it starts in the liquid. We want to make sure we really know which index we're finding. We're finding the first index of refraction. And putting numbers in, you should be getting 1.20. From here, it's a simple substitution into Snell's law. You should have no problem getting to 79.4 degrees. Part B, you want to find its wavelength in air. So here we have a couple choices. If you haven't done it yet, pause the video, discuss with people around you, try some things out, then come back to the video to see how I suggest doing it. As I mentioned, there's a couple choices. Certainly, we could use this equation which we derived in class for index of refraction, which we just found is 1.20. Remember, lambda naught is the wavelength in vacuum, or in this case, wavelength in air. It's the same deal. Lambda n, that's the wavelength in the medium. That's the 313 nanometers. Alternatively, nothing wrong with C equals F lambda naught. Now we can use this one, because this is lambda naught, and that is the wavelength in vacuum, or air, as it is. Oh, but then you say, wait a second, what about the frequency, right? We're given the frequency in the liquid. This would involve the frequency in air. But hopefully you remember, of course, even when light or any wave changes media, the frequency does not change. So whatever frequency we have here in liquid, that's going to be the exact same frequency as is in air. So we can go ahead and use this equation. So use either one of these. We should be able to get 376, I think possibly 375 nanometers, depending on which equation you use. But obviously we know 375 and 376, they're the same thing. All right, let's backtrack on our problem set. We're going to look at number 16. So go ahead and read this, try it out, people around you, pause the video, come back to it when you want to look at a solution and some discussion of the problem. Okay, so hopefully, of course, you started with Snell's law, N1 sine theta 1 equals N2 sine theta 2, and you should have found theta 2 as 23.4 degrees. But notice that's theta 2, right? N1, that's the first medium, is air, and 2, the second medium, is glass. So really what we did was we found this angle here to the normal. That's 23.4 degrees, and that's not what the problem asks us to do. The problem asks us to find theta 3, the angle when it comes back out into the air, because the light keeps going, right? It reaches another boundary, it's going to go again. So if you haven't done it yet, go ahead and draw a normal there, and then make a prediction as to what the light should do as it then reemerges from the glass into the air. In other words, complete the picture like we've been doing. Normal by definition, of course, is perpendicular, so here we draw another normal. It's at a second boundary here. Remember, we draw as a dashed line because it is imaginary. There's nothing actually there. And then we say, okay, as the light goes from the glass into the air, is it speeding up or slowing down? And of course, it's speeding up because it's going to air, which goes to a vacuum. And you say, does that mean it's bending towards or away? And of course, remember, it's bending away. So we should be drawing something like this. We don't know exactly how much it's going to bend away, but something to a larger angle. Now, if you're having trouble visualizing what's a larger and smaller angle, you know what you could do? You can just take your picture and turn your paper. If you need to see it go from top to bottom or bottom to top to see that, do what you need to do. Other students can just see there's a small angle, there's a large angle, there's a normal. It's up to you. But, do what you have to do, whatever makes sense to you. Okay, so now we've got to do Snell's law a second time. We're going from our second medium to our third medium. So really we should write Snell's law because we're finding theta 3 here. And there's theta 2 over there, right? As n2 sine theta 2 equals n3 sine theta 3, where now this is playing the role of the incident angle and this is playing the role of the refracted angle, which is what we're looking for. But now we run into an issue. This angle you found at 23.4 degrees is over here. We don't want that angle. We want this angle here. And if you haven't thought that through yet, pause the video, discuss people around you, and figure out how we're going to find that theta 2, this incident angle, at this second boundary. Well, you may have sort of happened upon it by luck or by chance, or maybe you had a good discussion and realized, well, we can use some geometry here. Considering it's a rectangular prism and the sides are parallel, if this side is parallel to this side, and this is a line perpendicular, another line perpendicular to sides that are parallel, well, we know from geometry we can use some alternate interior angles, right? It makes the z, so this angle theta 2 is the exact same as this angle theta 2, and so we can proceed from there. Now, remember, this only works because the sides are parallel. I was nice and gave you a rectangular prism. I didn't have to do that. It could have been some other shape there, in which case you'd have to do some fancy geometry to figure out what angle would be over there. But, you're all very good at geometry. It's how you got into this course, and so I'm sure you'd have no problem doing that. Okay, so you put this in, and hopefully you get a final answer here of 40.0 degrees. At this point in class, I'd say, well, wait a second. Do we really have to find 23.4 degrees theta 2 inside the medium? Really, we don't have to, right? There should be a way to get this final answer in one shot. So if you haven't thought it through, pause the video, discuss people around you, and come back to the video to see how I would go through it. Alright, so hopefully you realize that this says n1 sine theta 1 equals n2 sine theta 2. And over here this says n2 sine theta 2 equals n3 sine theta 3. Which means if A equals B and B equals C, then of course you know A equals C. That's called the transitive property. Right? So we can be able to jump straight from the first part of this equation to the last part in one shot and not even worry what happens in between. Now notice what I did here is I said equals ... which means it can keep going. Right? This could be n4 sine theta 4, n5 sine theta 5, and so on and so forth, meaning that if I just kept stacking medium after medium after medium after medium, I can jump straight from the first to the last and not worry about anything that happens in between. Now, this only happens if all the sides are parallel, right? Because the sides being parallel is what allows us to do the alternate interior angles. If these sides were at different angles to each other, we wouldn't be able to do this. So, if all the sides are parallel, we just keep stacking medium after medium after medium, we can jump straight from first to last in one shot. Although, that's not exactly true either, because you should notice that the light, while it does change direction, is always heading in the same general direction. Up and to the right, up and to the right, up and to the right. Can you see that if we keep stacking medium after medium after medium after medium, and if this is the upper edge, well, eventually this ray of light will cross over that upper edge. At which case, of course, the upper edge is not parallel to this side over here, in which case you certainly can't jump from first to last in one shot. You would have to do some other geometry like we discussed before, and figure out the new incident angle and do a refraction problem there. Okay? So, as long as we have all these media stacked in a row, and all the sides are parallel, and the light continues in the same general direction without crossing over another boundary, that's when you can jump straight from first to last in one shot, and not even worry about what happens in between. So that's a really nice shortcut. But if you look at our answer, you'll notice something even more interesting. I hope you already noticed, right? When you compare this answer to the original angle, you see they're exactly the same, which means really we should change our picture to show that it comes in at 40 degrees, it gets shifted, and it leaves at that same angle, just, parallel lines. Imagine extending the 40 degree, the incident ray through here, to be parallel to this exit ray. Now, why did that happen? Well, pause the video and discuss. So hopefully you realized this happened because light started in air and ended in air. So if we jump straight from the first medium to last medium, and N1 equals N3, then of course theta 1 has to equal theta 3. So if you have a whole bunch of media all stacked together, and all the sides are parallel to each other, and the light continues in the same general direction without crossing over the boundary, and the light starts in one medium and ends in the same medium, well then, you don't even have to do the problem, because whatever angle it comes in at, it will exit at the exact same angle. But that's a lot of ands, right? So just be aware that's not going to happen all the time. Now, does it really happen? Well, here's a picture I took of the laser light entering a rectangular block of plastic, which I have in class, and we do see this brilliance reflected, right? That's not what we're looking for, though, right? So it enters the block of plastic. It bends. Here would be the imaginary normal. It bends towards the normal, just like in our picture in the problem. It reflects again, which is cool, and comes out, but that's not the important part. Here it is exiting into the air. And you should see, here's our entrance ray, here's our exit ray, and they certainly are parallel to each other. So whatever angle it comes in at here, it leaves at the same angle on the other side. So yes, it really does work. Pretty cool stuff.